Okay, then let's think about what will happen when the potential is applied to the electrode. So let's think about the case when this part, the N-type semiconductor has a Schottky contact. This is a typical case for N-type semiconductor. Okay. So what you have to think about is now originally the Fermi level is the same as the chemical species potential. And then applying the potential change the Fermi level of the electrode. Okay, then here. So this one also, please stop video for a while and please draw for yourself about what will happen for the band diagram. Okay. So first, anodic potential was applied. Is applied. Potential. So by applying the potential, the originally same level of Fermi level is shifted downwards. And due to this downward shift, the original band, so band is highly bent. Actually, this bending of the band is called band bending. Okay, so this is when the positive anodic potential was applied. Okay, and I would like to emphasize that the when the electron going backside, this is a positive current. And in this situation, you could see as we studied, some of the charges are excited in the N-type semiconductor due to the thermal excitation, but very minor, very small, but it's going to the positive current. And also some of the very minor holes are going into the solution side. That's what happened for the anodic potential is applied. So in this case, you could see because there's no not so much diffusion current. Diffusion current is when a diffusion current is the opposite way. So only the drift current is possible by thermal excitation. That's why the current itself is small. And this current direction is hole is positive charges coming to the solution side. So this gives oxidation due to this hole happen for the solution side. Okay, that's what happened when the anodic potential is applied. On the other hand, in the case of cathodic potential is applied, so again, the chemical species have the same energy level, and then original Fermi level is now shifted upward. And similarly, the band is gradually shifted like this. Okay. So now what? Since this is an N-type semiconductor, has many electrons in the bulk, and for this electron, it's easy to come to the interface, right? Because there's no barrier due to the ohmic-like contact. That's why the current itself is now large, because this current is originally from the diffusion current. And I'd like to note that this electron current is different, opposite from the anode when the anodic potential is applied. So this is the large current, and since this is electron, this is a reducing ability. So a strong reduction current is induced. So based on these aspects, we can make a total current voltage dependence in potential and current. So when the anodic potential, meaning positive current, positive potential is applied, the charge electron is moving toward going outside, but this is a small current due to the thermal excitation. And since this is a drift current, it's almost constant, right? Like this. And when the potential is applied at like cathodic potential, now the electron current is getting larger, and depending on the applied potential, because this is a diffusion current, it's exponentially increasing. So by connecting these two, something like this happen. This could happen. So this is the potential current dependence for the N-type semiconductor electrode. Okay, and also I'd like to mention that this kind of consideration for contact between the semiconductor and the solution is applied for P-type semiconductor too. And I give the exercise after lecture for P-type case for yourself. Okay. Now, let's think about the water oxidization case, and especially for light irradiation, called the water splitting, because water is changed to oxygen or hydrogen. And let's see. First, this is a basic equation. As you know, the water is oxidized to oxygen, and just using the electrochemistry, you need potential of 1.23 volt versus SHE. So if you apply the electrode 1.23 electron volt, no, 1.23 volt, you could split the water to oxygen. Water to oxygen. Okay. And let's think about this. Again, let's think about the case when we use any N-type semiconductor. Okay. So when the N-type semiconductor has a contact with solution or water, so as I mentioned, most of the N-type semiconductor shows a Schottky contact. And at this moment, we don't know where the redox potential of water compared with the N-type, because I didn't specify some material. And the redox potential for water changed to oxygen, it's 1.23 volt. Right? And as I mentioned, for for the N-type semiconductor, and this has some band of bending position like this, and even for this small in this depletion region, so small number of charges are excited by thermal excitation, which is called drift current. So electrons going this way. But as I mentioned, this is basically very small number. So since this hole has oxidization ability, you can oxidize water to oxygen. But again, this is a small number, so very less. And for electron, it cannot go this way because it has Schottky barrier. So mostly electrons going this way. So if you don't use light, basically nothing could happen. However, in this situation, if we have a light, the situation is totally different, because now now we can use light instead of thermal excitation. We can effectively increase the hole and electron excited in the depletion region. And these holes can oxidize water. So now large number of hole can oxidize the water. So by combination was this. So what happened for this IV curve? Originally, it was something like this, right? However, by using the light, this. So I would like to emphasize that this is a drift current. So drift current can be pushed up to a higher level by light. So this could be possible. So this is the basic concept how to utilize the light for photocatalyst. Okay, then let's review the N-type semiconductor case, and then please stop the video and draw what will happen for each applied potential case. Okay. So let's draw again here. Now, when the potential applied cathodic potential, so that's negative, right? Cathodic potential is applied, so it's going to be chemical species and the Fermi energy and something like this. This for electrons can go to the solution side to generate a current exponentially increasing. So this is ohmic contact. And on the other hand, when you apply the anodic potential, the potential, the Fermi level is lower. So that's why, like this. However, the current itself is only due to the thermal excitation. The current is small, but the positive current you could observe. On the other hand, if we apply here light, so many electrons and many holes are generated, and this hole can easily go to the solution side, and then electrons are moving backward to the electrode. That's why you could see the increase of the drift current. This one drift, some small drift, large drift current. So this is a summary for the N-type semiconductor electrode, and when the light is applied.